Hey everyone! In this talk, we're going to build Concurrent React from scratch. My name is Six, and I'm happy to be at ByteConf React 2020. In fact, I've given a version of this talk before in London, so this is actually version 2 of the talk, hopefully bigger and better. So here's a list of things that we're actually going to cover. It's a lot. We're going to cover what React Fiber actually is. We're going to cover linked list traversal, how React renders and then commits. We're going to cover how to write our own useState hook. We're going to cover what a work loop is and why it's so important to React. We're going to cover the create root API, time slicing, and suspense. The last two are kind of marquee features of Concurrent React. That's what you think of when you think about Concurrent React, but really all of the React features that have come out have been a result of the React Fiber rewrite 4 years ago. So we're just seeing the implications of what that means today. So it's very powerful and it's very fundamental to understanding what React really is. Before we get too far, I do want to acknowledge the people who made it possible for me to give this talk. There's no way I could have figured this out on my own. The primary resource you should check out is Rodrigo Pombo's Didact, in which he wrote a series of articles explaining to you how to build your own React. This talk is essentially a simplified version of that project. And in terms of understanding what React Fiber really is, I'm indebted to Andrew Clark and Lynn Clark, and I'm going to share those resources in the chat. Okay, so we're going to start by explaining what a JSX element is. It's really just a plain old JavaScript object. It has a type and it has props. So if you try to put it in code, it kind of looks something like this. I simplified it a little bit, but that's an h1 with a hello world as child. And that's really all the data that you need to represent HTML in JavaScript, which is essentially what JSX really is. So now that we understand what a JSX element is, let's actually try to write it out and render it onto the screen. We're going to start with an empty JavaScript file. I'm just using Webpack to import some CSS, so we have some nice animating background over here. And this is literally the only JavaScript that we're running. For example, here I can write a console log, and it logs out here with nice hot reloading if I ever need it. So it's a nice development workflow. So the first thing we want to do is think about how to render a text element. We're going to write it from absolute scratch. So for example, here I can define a text L. It's an object with a type of text element and a props, which is a node value, because that's how the DOM defines text element. I know it's a little weird. Everything else is value, but this is node value. I also need a container. So container, I know just from setting up the HTML that it is get element by ID root, and that's the ID I've assigned to it. And finally, I need to render it. I have pre-prepared a render function. So it's going to import from utils over here. I'll show you that in a minute. And then we'll type text L and container. And that will just give it the arguments that it needs to render it onto the DOM. So that's great. That's something showing up on screen. Let's actually have a look at the source of the render function. It's pretty light. It's only about 17 lines of code, and basically just says, for example, if the element type is text element, we'll create a text node using the JavaScript API. We'll add any props that we want, for example, like the node value, and then we'll recurse for all the children, but we're not really using that right now. And then we'll append child to that container that was supplied to us in the render function. So pretty simple. We don't really need React yet, right? It's still a little bit of a hassle to type this object every time. So it'll be nice to actually have a nice utility function for that. So of course we have that. We can create text element, and that auto imports from utils as well. And let's have a look at utils and what the source of the create text element is. And it's just a nice simple function that returns the object that we were handwriting anyway. Of course, when we write HTML, most of the time we want to write HTML tags. So we need some way to represent HTML tags. So let's actually see what that looks like from an object basis, like a type of h1, for example, and then a props with an object as well with children, which is always an array, and then text L. So I've put text L as a child, immediate child of this h1 tag. And I can place that in my render function, and that should refresh nicely to an h1 of hello world. This is what we typically think of as an h1. It's actually a combination of an element and a text element. So of course, writing this as an object is kind of ugly. Let's actually tighten that up a little bit. So let's actually use create element. That's going to take a type of h1. It's not going to have any other props, and it's going to have a child of text L. And that's going to show up exactly the same. Let's take a look at the source of create element. It's pretty similar to create text element, except it has a dynamic type. It spreads the props, and it has all these children, and some of them, if you're just supplying a string, it helps you create the text element in line. Of course, this is nice, but what's even better is if we could use JSX. So over in this project, fortunately, I've enabled Babel. Notice that these are the only dependencies. I have no other dependencies. And I have Babel preset React, which has the JSX transform. Instead of all these function calls, I can actually delete all of that and pretend that I'm writing HTML. And I can say hello world. This still isn't good enough because JSX transforms to React.create element. So we actually have to define an object, and we'll just call it React. We can call it other things, but then we'll have to change the pragma. We'll just call it React.create element, and then that should work fine. So here we have a pretty good representation of how it is to write JSX and render it to the DOM. We create the element, we write JSX, and then we add it to a container, and we append it to the DOM. And because the render method is recursive, like I pointed out earlier, we can actually swap this simple element for something a little bit more complex. So here I have an app with a bunch of children, just for illustration, and I can actually type JSX as the element in line over here, and that should render out this app. Okay, so we fully explored what JSX elements look like under the hood. They have a type and a props. In real life, they also have a key, and you can toggle any one of these, the type of props or key, to trigger a re-render of that element. So now we're going to go from elements to fibers. And let's actually look at the difference between elements and fibers. So React Fiber is actually a data structure that's a superset of the elements that we've explored so far. For example, if there's a matching DOM node, we're going to add a reference to that DOM node in the object itself. Then we're just going to add a bunch of properties that are basically links to other fibers around it. So for example, its immediate child, or its parent, or its sibling, or its alternate version of itself that's being worked on in progress. We'll talk about that one later. Finally, we're going to include an array of hooks that basically store the states and effects and refs and all the other good stuff that you're familiar with hooks, as well as an effect tag, which is a marker from the reconciliation process, telling us, hey, when you commit this to the DOM, there's actually some DOM nodes to be created or some DOM nodes to be updated in place, or you should just delete them altogether. So the effect tag helps us separate rendering and committing. If you put all these concepts into a plain old JavaScript object, it will kind of look like this. It's got all the element stuff that you're familiar with. Then it's got all that linked list stuff to other fibers neighboring around it. Then it's got hooks and it's got an effect tag. So now we know what fiber is. Let's actually remind ourselves of why we want to use it. So currently we're rendering this app, right? And the way that we render this app is a pretty simplistic process of recursive render and commit. So here we start at the root, right? And then we head to the div, we'll render that, and then we'll commit it to the DOM. We'll head to H1, we'll render that, commit it to the DOM. And at any point during this process, a user can come along and see a half committed DOM state. And this is inconsistent with the rest of the app, which hasn't been completed yet. So the solution to this is to render everything first and then commit. So here we'll do the same thing that we did before. We started the top level, but now we don't commit to the DOM. We'll actually just perform that rendering work. So here we'll just call it perform unit of work. And then we'll proceed to the next child without committing to the DOM. So we're doing all these changes only on the fiber data structure. So we'll go to the child, then we'll go to its sibling. And meanwhile, if any user comes along, we haven't committed to the DOM yet, so it's still good. It still looks like the old version. And all this changes and diffing is only happening in the background on the virtual DOM. Then we'll head to our child again, and then we'll head to its sibling. And when we've run out of children or sibling or aunts and uncles, then we can recurse all the way back up to the root. Now that we know there's no more reconciliation work to be done, we can actually commit everything to the DOM, which is in contrast to the commonly held belief that we use virtual DOM because committing to the DOM is expensive. It's actually reconciliation and rendering that is expensive. If you want to learn more about the fiber traversal algorithm, head to React issue 7942, where Sebastian actually listed all these in greater detail. But for now, let's try to swap our implementation over to take advantage of rendering and then committing. Now this render is a little bit too simplistic. It just kind of goes through and renders each element in turn straight onto the DOM, and that affords us no opportunity to diff the DOM. So what we actually need to do is start to create a virtual DOM structure using React Fiber as our data structure. So for example, I'm going to introduce the concept of a work in progress root fiber, and we'll just call it WIP root for now. And we're going to start to populate this in order to replace our render method over here. So the work in progress root fiber is an object. It typically has a type, but at the root, we don't really care about a type. It has a DOM equivalent. So here our DOM equivalent is the container. It has props. Here we're just going to hardcode the props to have children of app, for example, which is exactly what we're doing up there. And then it has other optional stuff. So for example, it has links to other fibers that its siblings, that our render traversal algorithm can pick up. So for example, it has a child fiber, it has a parent fiber, it has a sibling fiber, and what we're eventually going to get to is that it has an alternate fiber, an alternate version of itself, where that's the one that's rendering virtually, and then we'll swap it out. But for now, we don't need any of this, so we'll just keep it simple and call it the work in progress root. Okay, so what is work? We actually have a good definition of work in this context. Work is basically the work involved in rendering each of these elements individually. Basically, what we want to do is have an algorithm that traverses down this tree structure, does all the processing and render work, and then traverses all the way back up. And only once all of it's done, then we commit it to the DOM. So we'll define a pointer called the next unit of work, and we'll set it initially equals to the work in progress root. So we start at the root, right? And basically what we need is a method that just processes the top level div and then returns the next unit of work. And we'll take that pointer and then we'll process the next child, and then it will return the next unit of work, which is the UL. Take that pointer, process the next child, and return the next LI. So that's the rough traversal algorithm that we're going to follow. So instead of a simple paradigm of rendering an element straight all the way down and directly onto the DOM, what we want to do over in the fiber section over here is that we want to be able to say, okay, we'll start with the next unit of work in the work in progress root. Then we'll perform the next unit of work. And we'll get back a reference to the next unit of work to be done, which is starting from the top and going down all the way. And while this next unit of work exists, we'll just keep doing it. And only after we're done doing all of that, then we'll commit that work to the DOM. And the thing that we're going to try to commit is the work in progress root child, which is the first element, which happens to be a div that precedes all of this stuff. We're actually rendering 2 copies of this app over here because we have a simple render and then we have the fiber render. So we don't really need the simple render anymore. I'm just going to get rid of that, as well as get rid of that from the imports. You notice in writing that code, we actually imported 2 more functions, perform unit of work and commit work. So let's actually take a quick look at their implementations. So this is what happens when we actually perform a unit of work. We branch on whether it's a function component, so we can just call it, if a function component's type is just its function, or it's a DOM node, so we just call the create DOM utility that I have defined below. Both of these paths end with reconcile children, which is a simple function that turns elements into fibers, as well as diffs fibers against fibers, and generates an effect tag. So either something has been updated, something has been created, or something has been deleted. When we're done with the rendering work, it's time to return the next unit of work. So either if there's a child, we'll return the next child, or if we have a sibling, we'll return the next sibling to do work on, or we'll recurse up to the parents and let our parents take care of their own siblings, our aunts and uncles. So that's performing the unit of work. Let's actually look at what happens when we try to commit that work. We're basically going through all the fibers and saying, all right, reconcile children has placed an effect tag on the stuff that needs to be updated. Let's go through and say like, if something has been placed, for example, like a new DOM node has been created, we're going to append child. If an update has been tagged, then we're going to update that existing child in place. So we're not deleting it and then recreating it. And if something has been deleted, then we'll also delete it. So here are all the helper functions available. And this whole utils folder, that's it. That's all the utils that we're going to need. It's only 177 lines long. So that's not too bad for the backbone of our new framework. So now that we've understood what perform unit of work and commit work do, and we have a concept of what rendering is and how we do all the render work, and then we commit it to the DOM, let's actually wrap this up into a nice render function that we can use. The API that we want is the same that we had before, which is basically render an app into a container. So let's define that render function. We'll call function render. It's going to take in an element and a container. I'm going to prepend it with an underscore so we don't conflict with that real container for now. Then we're going to take everything that we've just done and we're just going to cut and paste it inside of that function. So now we have a nice abstraction so that when we just call render L container, that should show up on the screen. We actually need all these declaration of pointers to be at the top of the module so that we can actually reference them. So let's take that and paste it up in here. And then we should get back our original methods. The difference of what we've just done is refactored our render function from a simple recursive render into something that is fiber aware, that renders all the work, and then it commits only the differences. Now, of course, to enable Concurrent React, we actually don't use this simple render API anymore. We actually have something that looks a little bit more like this, create root container dot render on an app. And this enables other methods of rendering, like, for example, blocking rendering. So let's actually refactor this API. It's pretty simple. We're going to define a function of create root, and it's going to take that container, same as always. But it's going to return an object with a render method that takes that element that we had before. So now we'll just take the contents of this render function, cut it out, and we'll paste it in here. And that should work fine for the create root. So now if we delete our old render method and call the create root function, it's going to work the exact same way and show up. It's just a refactoring of this API so that we can offer other render APIs as well. Awesome. We now know how to implement the create root API, but inside of the create root function, we only render things once from top to bottom, and then never again. We commit the work and then we're done. So essentially we need a way to loop through and re-render until the end of time. So that's what we're going to write next, which is the work loop. It's basically an infinite loop that doesn't hang your computer, which is very nice. The reason it doesn't hang your computer is because we're cooperatively scheduling our resources between the browser and our JavaScript. However, a simple work loop isn't enough. Because rendering is expensive, for a large DOM tree, you might actually choke up the browser while rendering your entire thing before committing to the DOM. You want to actually be able to pause and resume rendering. So that led to the idea of time slicing, and that's actually what we're also going to look into next. The differences between synchronous rendering, which is what React has today, and time slice rendering, which is what Concurrent React has, is pretty dramatic. Here's a screenshot of a talk of Andrew Clark. This shows the differences between how React works in synchronous mode and as well as async mode, which we now call concurrent mode. In concurrent mode, our rendering yields back to the browser every 16 milliseconds so that we're always able to receive browser events. So this makes our apps feel a lot more responsive to user interaction. This is a major source of jank in React apps today. The benefits of time slicing aren't merely theoretical. I encourage everyone to try out the Sierpinski triangle demo and use the browser dev tools to verify this for yourself. Here we've got two examples. One uses the stack reconciler, the old synchronous reconciler, and the other uses the fiber reconciler, which is the new proposed reconciler. We can open up the stack demo, and we can see that the updates are kind of janky. They kind of update bit by bit. And even worse still, the circles are supposed to respond to my interaction. Like when I hover over them, they're supposed to just turn yellow, but they just take a long while and they kind of trail far behind where I am. If you open up the performance tab and you hit record on this, you can see large chunks of rendering work spreading out over hundreds of milliseconds. Let's take a look at the equivalent for the fiber example. So over in the fiber demo, you immediately see that the rendering is much smoother. And when I hover over these circles, there's very little delay. So that's very positive. Let's actually look at the performance tab and also do the same process of recording a little bit. And when we look at the performance tab, we can see a lot more choppy graphs, which means that the rendering process is yielding back to the browser, which enables for all this rendering and user interaction to work smoothly. So the benefits of time slicing is real and is immediate the moment we enable create root in Concurrent React. For more details, you can check out Brandon Dale's benchmarking of this in this Twitter thread, which I'm going to paste in the chat. The main mental model that you should have in your head is that when we combine time slicing with a work loop, we're basically saying that we render until we run out of time, and then we'll pause and yield back to the browser, and then we'll resume again with the work loop, and then we'll render until we're done, and then we can commit all the way at the end. So let's try to implement that in our app, and along the way, because we want to see something update live on our screen, we're also going to implement a useState hook. So now we want to implement a work loop, and a work loop is kind of like a function that just calls itself again and again, similarly to a game loop, if you've done any game programming, which I haven't, but that's apparently what it's like. You might typically run a work loop with something like set timeout. So we can call work loop from within the work loop, and we can set timeout to once a second, and we can call that same work loop from outside of the work loop, so it can just keep running itself. And let's actually see that pop up in our console over here because it's fun to watch. So here, every second, it's just going to pop up a new high. Great. So now basically what we're going to do is we're going to take out the rendering work from the create root function. I'm just going to cut this next unit of work stuff out. And we're just going to keep doing this every single work loop, right? We're just going to say, if there's a next unit of work, then we'll perform all that unit of work. And then once we're done, we'll set a timer for the next thing, and every second we'll start reconciling these changes. So instead of setting a work loop, we're actually going to use a request idle callback API. The reason that we want this is because request idle callback gives us an idle deadline, and we can call the idle deadline.timeRemaining function to give us a timestamp of how much time we have left in the current rendering frame. So this lets us time slice very well. So we'll take a deadline argument from request idle callback, and we'll try to calculate whether we should yield back to the browser or we should continue our work. So we'll say something like let should yield. By default, we'll say it's false, but we'll basically calculate should yield whether deadline.timeRemaining is less than 1. And if should yield is false, then we should continue doing our work over here. If should yield is true, then we should pause what we're doing and yield back by just calling request idle callback again. We should also not commit our half done work. So basically we should check whether there's still work to be done, like say next unit of work over here. And we'll still a commit work function inside of a check for whether there's a next unit of work. So in case we've paused our work to yield back to the browser, we don't accidentally commit our half reconciled work and undo everything that we just did. All right, I really want to see some dynamic stuff on screen. So we're going to start implementing a hook. So the first thing we want to do is implement a hook index. So all hooks are just positions in an hook array. And we want to modify our fiber data structure to have the concept of a hook array. So over here in our creation of the work in progress root, we can say something like hooks is an empty array, as well as the alternate version of our fiber, which we're going to also start to want to need, also should have hooks. So now we created the concept of an alternate fiber. Every fiber has its alternate, and we'll do our changes onto the alternate version before swapping over to committing to the DOM. This is important for us implementing useState. So here we're going to implement useState. So we'll declare a function useState. It's going to take an initial value, and that's about it. Now hooks are a bit unusual in that they're basically functions with some memory. And the way that we achieve that is you're basically pulling the old state based on the alternate version of the fiber that we're currently working on. So I've pre-written a bunch of that code so that we don't have to write it manually out. But let's actually kind of go through that. So essentially what we're going to say is that the old hook is actually picked off the work in progress root fibers alternate. And we're cheating a little bit by storing all the hooks on that single fiber. Ideally, every single fiber has its own list of hooks. Here, we're just co-locating everything onto the same fiber. And we're using the hook index to that specific hook that we want. And once we're done with that index, we'll increment it by 1 for the next hook. Then we'll look at that hook and we'll check if it has some pending state. And remember, this pending state could be null or undefined, so we can't really use falsiness as an indicator. So we actually have to use a symbol for none, and the symbol is and that symbol is not going to match anything. So we can actually just safely check this. And we're likely to use this between calls. So we actually need to elevate this none symbol to the top level so that we don't redeclare symbols. Otherwise, they're not equal to each other. And the last thing that we need is the old state. So we'll just look inside of the old hook. If there's state in there, we'll take that state. And if not, we'll take the initial value that was given by the use state. So finally, our new hook that has been derived from all this data has a value of state. If there's a pending state, we'll take the old hook's pending state, which means that there was an update called by, for example, calling set state. If not, we'll just take the old state that was there before. And then we'll just say that the pending state of this is none for now, which is the same symbol that we used earlier. So with this done, we can actually write the remainder of use state, which is the interesting stuff. So for example, we can write the set state function, which takes a new state, which you give it, right? And it just appends it on the pending state of the current hook that we're operating in. So we're using closure to retain a reference to this hook. So even regardless of what fiber we're on, we can actually just directly append onto this hook, which is a very nice and convenient way to do this. Then we'll also need to schedule a re-render. And this basically says, okay, we actually now have a new unit of work to do. Let's go through and reconcile all the roots again with this new state. We haven't implemented this yet, but we'll get there once we're done with this hook. We also need to append the newly created hook to the work in progress roots hook array so that we can actually pull it off in the next run of this. And then finally, we can return that API of hook.state, which is that state that we just calculated, as well as setState, which is that function that people can call to set the state of the hook. So now we're actually implementing something that's dynamic, that actually says we're going to do all the state modification on one root, and then we'll reconcile it, and then we'll swap the roots over. So now we're actually forced to implement a current root instead of just a single root. So we'll say current root over here, and this is just a pointer. And inside of the work loop, we're going to assign to that current root, and we'll say after we committed our work, we'll assign a work in progress root fiber to the current root, like we swapped that fiber over. We're going to set our work in progress root to null because we are done with it. And we can say our hook index is 0. So we restart the index from 0 so that we can increment it all the way. Now, because we set the work in progress root to null, we also need to set a safeguard here because otherwise we'll try to access the child of something that doesn't exist. So we'll just say if work in progress root is truthy, then we'll allow this committing of work to proceed. So now we've implemented a nice swap of like, we'll do all the work on work in progress root, and then we'll swap over to the current root, and then we'll nuke the existing work in progress root. But we haven't implemented this schedule re-render function. So let's actually see what that looks like over here. So with the schedule re-render function, we're basically saying we want to take all the properties of the current root and clone it onto the new work in progress root, which we're manually going to set. And then we're going to set that work in progress root to be the next unit of work. So when the work loop picks up its next unit of work again, it says, oh, I have something there to do. I'm going to start at a work in progress root and just continue all the way down, just like we did before. Okay, so that was a lot of work to implement state. But now let's actually see this in action. I'm going to fold all the code levels, open up our app again, and try to implement a simple useState function. So here I'm going to say state and set state, pulling off of the useState that we declared earlier. And we're just going to give it a value of 1 to start with. So let's have a button over here, and it has an onClick that sets set state to state plus 1. We can close that button and actually show the value of state as well. So now you have a pretty intuitive understanding of how this useState hook functions. When I click this button over here, it calls setState. And that setState is the function that we just worked on, which is it sets the hook's pending state to this new state that was given, which is state plus 1, which is now 2. Then it schedules a re-render, and React just starts back with its next unit of work all the way up to the top, and it just goes through and finds that the thing that's changed is that this hook has the new state. Of course, you can just do this with just functions, which is the subject of my other talk. But now you have a concept of how this works in terms of fibers itself. And remember again, ideally, that each fiber has its own array of hooks. Here we've just implemented it at the top level for simplicity. Okay, we've done quite a bit. So far, that was about 82 lines of code. And we've mixed some app code together with some framework code. And the last step to creating our own framework is basically extracting this into its own file. So here I'm going to create a new file, and I'm just going to call it something silly like react.js. And then I'm going to cut a lot of this stuff and just paste it inside of react.js. I'm going to delete the app-specific stuff like the CSS, like the app over here, and the create root call. And then I'm going to expose the stuff that I'm going to need. So I'm going to expose create root, and I'm going to expose useState. And then I'm going to export the entire React module itself. So over in my app code, I can do the same thing. I can just delete all the library code and just keep all the app-specific code. And I can say import React from ./React, the one that we just hand wrote. And we'll just say react.useState over here, as well as react.createRoot over here. And that should show up exactly the same way as it did before. Except this looks like React. We have hooks, we have JSX, we have rendering, with everything that you usually use. And that's a pretty nice result, isn't it? All right, now that we've implemented our own little React clone, we really understand the significance of this render then commit cycle, the way that we do all the reconciliation on a virtual DOM, and then we commit everything in a final step. And that lets us update the DOM using a set state on a component, and using time slicing, cooperatively schedule with the browser so that our rendering work doesn't conflict with user interactivity. And only after everything is rendered, then do we commit everything to the DOM, and then using the work loop, we'll wait for the next thing to happen. So that's almost everything I wanted to cover about Concurrent React, except for the headline feature of Concurrent React, which is Suspense. And we have a little bit of time left to implement a clone of that inside of our app. All right, we're in the home stretch. So for the purposes of demoing React Suspense, we need a little backend to query against. You can obviously mock that on the front end, but for my purposes, I actually implemented that in Darklang just because it's cool. And here, basically, we have a list of strings. And you can pass in a query params of count and take, one or more dogs from that list of strings. So essentially, here's how it looks like as you query it. You can have
one dog, or you can have count equals 3 and you get 3 dogs, or you can count equals 6 and get 6 dogs. You get the idea. All right, so normally you would take this API and you would go into your code and you would do something like react.useEffect, which we don't have yet. And then you would have some kind of fetch here, and then you would say fetch API, and then you would have the state down in here, and then x.json, just because that's how it works. Then you have the dogs data, and then you have to set dogs. And of course, you'd have to implement this by adding another hook, purely for the sake of data manipulation. So dogs, set dogs, and then this would be an empty array. And then you would implement the dogs here. So like a dogs.map, dog with an image, and that would be that. We don't have use effect here, but that's the rough boilerplate code that you would have to do. And you would be waterfalling this request. So essentially you'd be rendering that app code, and then you have to fetch that data afterwards. So ideally you want all of this to just show up at once, because then you don't have to implement things like loading spinners. So what I've basically done is I've taken this fetch call and I've wrapped it inside of a function. And I wrap that function inside of a promise. And this promise is a special promise. It's basically a suspender. And essentially what this does is it exposes an object, and it gives you a read method. And the read method says, if the argument that you want to read is the one that I have already cached, then I can just return that result and call it status a success. If not, I'm going to throw a suspender, and the suspender is the thing that's actually a promise. The suspender says, we'll call the promise that was given, and the promise is basically the fetch dogs function. We'll call it, and we'll get that result, and then we'll set that result as our current cache. So it's a very simple cache. It only caches one result, but that's the minimal viable example that you're going to need for React Suspense. So essentially what we need to do is we need to rewrite our React render function to understand that when something is thrown, but it's a promise, then we should keep that promise result and then suspend all our work, don't render anything yet. And then when the promise is resolved, then we'll resume rendering again. Obviously, that's the most naive way of implementing it, but that will give you a good mental model of how React and React Suspense interact. So let's jump into our React module and think about how to implement this. Basically, we want to think about where do we do our rendering work? And at a high level, the place that we do our rendering work is when we perform a unit of work. And that's how we iterate through all these steps. And if any of them throw a promise, we should cache the promise, wait for the promise to resolve, and then re-render it again. So basically what we're going to do is we're going to wrap this line of code in a try block, right? And we'll catch, and we'll check that error, and we'll say if this error is an instance of the promise, then we'll stop our rendering work because now we have to suspend, right? So we'll set the next unit of work to be null, and we'll wait for that promise to resolve. So error.then. And once the promise is resolved, we can just set things back to where they were and let React re-render again. So let's see how this improves the way that we work. So over in our dog API file, we exported a function called create resource. So I'm going to import that from dog API. And I'm going to create that resource outside of my function. So resource goes create resource. This is the recommended API by the React team. And instead of all of this code, I'm just going to delete all of that. And I'm just going to say dogs equals to resource.read that current state. And now this actually starts showing up. So we no longer have to do that asynchronous dance between our effects and then we'll define an extra state. This is all just taken care of us by just having an external resource that caches our result. And we can suspend on it asynchronously, just like we can synchronously read from our hooks. So now you can see in my app, when I click next to increment that state, the resource also suspends, fetches that data, and then resumes, and then returns that result to me. So I don't have to do any of that asynchronous stuff inside of my code. It's all just synchronously reading either from the React runtime, which reads React hooks, or it asynchronously reads from the external created resource, which caches our results. And this is how you get a bunch of very good boys. So we implemented something that looks pretty close to React Suspense. It has the exact same API. I maybe fudged things a little bit with the parametric read. But essentially, this gives you the right mental model. And it's a lot easier to interact with data using React Suspense, which I'm very excited about. You also get some very good boys just by interacting with this API, which is definitely a plus. Okay, I've given you some basic understanding of what Suspense looks like under the hood, but that's far from everything that you need to know about Suspense. You should check out the blog posts by Joe Savona on the React blog about using Suspense as someone who writes apps. And check out the 3 talks that were given at last year's ReactConf for more details on how to use React with best practices like render and fetch at the same time. I'll especially throw in a plug for Tanner Lindsley's React Query, which I think is the perfect data fetching library for using React Suspense. So we've covered a lot today. If you take a look back, over this past half hour, we've actually implemented everything from this list, from understanding what React fibers are, linked list traversal, rendering then commit, a hook, work loops, time slicing, create root API, and Suspense. But that's not even half of what React actually gives you out of the box. And that's the message I want to leave you with today, that you as a React developer benefit from all the dogfooding that is being done at Facebook, working on the largest app on earth, as well as all the open source contributions by everyone else who uses React, including ourselves. If you're looking to deepen your knowledge of React and appreciate what it does for you, look into all of these features which we couldn't implement in a 30-minute pre-recorded video. This is all the awesome value that you get out of it. In fact, if you're feeling up to the challenge, you can even implement some of these yourself, starting from keys, hooks, suspense lists, and even some fragments, portals, and context. The more you figure things out for yourself, the less everything will seem like a black box, and the more you can do with React. That's my talk, Concurrent React from scratch. If you want more talks from me, check out my site or connect with me on Twitter. And special thanks to Rodrigo Pombo and the React team for all the ideas here. I didn't come up with any of them. I'm just explaining it and learning it in public. If you have any follow-up questions, hit me up in the chat. I'll be around. See ya.